Hey, this is Mr. Ziegler here. I'm going to go through Monday's assignment for week 10. All right, so I'm going to click on gas variables and Avogadro's notes/sim. And I'm going to have a slideshow embedded here that I'm going to be using to take some notes. But I also have a worksheet here. So I'm going to open up this worksheet in another page, and then I'm going to kind of do this split screen thing. Let me move my head here. So I can see the notes on one side and I can see my notes or the notes on one side of my worksheet on the other. All right, so let's get started here. All right, so gas variables in Avogadro's law. First, we're going to start with some gas variables here. So pressure is a measure of the amount of gas particle collisions. And that could be a collision with another particle, or that could be with the container. So let me just draw a quick picture here. If I have a box and I have these gas particles in there, they're going to be moving around. Remember when we talked about solid liquids and gases, these particles are moving around and they're going to bounce sometimes into each other and into the sides of the container. And the more that they do that, the higher the pressure there's inside the container. And if the pressure inside the container grows to be a really high number, depending on how strong the container is, you can actually get a container to like explode. All right. But we're going to measure this in ATM, and that stands for atmospheres. So the atmosphere that we just live in has a pressure that's pushing down on us. We're not really we don't really notice that because we're used to it. Every day we have this pressure, and so we don't really notice it. Kind of like how a fish that constantly lives in water probably isn't very aware of the water that's around them until they get out of the water. Then they notice that something's different. Okay, so pressure, the symbol is going to be a P for pressure. The definition, whoops, maybe I'll just type in here P. There we go. Okay, the definition, a measure of the amount of gas particle collisions. Collisions is probably the big key term there. I'm going to underline and bold that. Okay, and then units measured in ATM. Oopsies, I put AIM. ATM, atmospheres. Okay, now I mentioned this before in some of my other videos, but if you would highlight everything and change your text color, could be blue, red, whatever, just not black. And that helps teachers, myself and Mrs. Hamlin, just kind of find your answers a little bit quicker and helps us give better feedback and grade things a little bit quicker so we can get things back to you a little bit faster and keep grades updated. All right, next is temperature. Temperature is going to be a T. Definition of temperature. Okay, we talked about this in our last unit. It's a measure of the speed. Sometimes we say energy because the energy is coming from the speed of the gas particles. Okay, and that can be measured in two different ways. Celsius, did I spell that right? Or Kelvin. Okay, now we prefer Kelvin, and the reason we prefer Kelvin is because we can't ever get a negative number with Kelvin. Remember, absolute zero is zero Kelvin. That's the coldest temperature you could ever have. And so if we ever do get Celsius, we're going to try to convert it to Kelvin, but you will see a lot of things in Celsius. All right, so these are properties of gas. These are things that gases do. So I talked about pressure with a picture. Temperature, I'll do the same thing. So if we have these particles, these arrows represent how fast they're moving. So a longer arrow, like this one here, means it's moving faster. And if it's moving faster, it has a higher speed or more energy, and that means that it has a higher temperature. So it's not that this actual gas particle is hot, it's how fast it's moving. So if we heat it up, that means we're putting energy into it and it just is going to move faster, and it feels to us like it's getting hot, but we're really measuring the speed. All right, last thing before I go to the next slide. Again, whoops, here we go, change that to red. All right. Here we go. All right, next, volume is going to be a V. All right, and that is a measure of the amount of space gas particles take up. Now, remember we talked about this. Gas has, we could say, a changing volume or an indefinite uh, volume, meaning that its volume can change. We can take that gas particle and we can stretch it out, or we can crunch it down, depending on the container and the situation that we're in. This can be measured a lot of different ways. Centimeters cubed. The way I got that 3 up there, instead of just making it look like this, all right, is I do control period. All right, and then I can put a 3, control period, to get it back down to normal. So I could get, whoopsies, there we go, centimeters cubed, milliliters. That's not a mistake. The M is small, the L is capital, or sometimes you'll see liters. All right, those are 3 different ways we could measure the volume. That's how much space it takes up. So depending on, again, whoopsies, here we go. Depending on the container. So some containers are flexible, like a balloon. Okay, and if we have these gas particles in here, depending on how much maybe they bounce into it, how fast they're moving, how many particles in there, we can actually stretch, all right, that container out a little bit more. And if we stretch that container out, there's a bigger volume, a bigger space that those particles have to take up. All right, let's highlight. Let's turn red. Okay, lastly, number of molecules, that is lowercase n. Okay, that is the count of actual gas particles. How many gas particles we have? It's a number, so it'll be 10. Usually we'll have a lot more than 10, but you could have 10, 20, 1,000, 10,000, a million gas particles in a sample or in a situation, a container. All right, and we are going to measure that in just number of molecules. So you might just see like molecules, or you might see something called moles. And a mole is kind of a package of molecules. We'll actually have a unit where we talk about moles a lot more, but kind of like a dozen is always 12. A mole is always a certain number, and it's a huge number. You don't need to know how much it is, but it's a way to compare how many molecules we have. Okay, change that to red. Okay, so that just gives us a little bit of background on some of the variables or some of the things about a gas that can change. Okay, so now let's go to Avogadro's law. Let's skip that. I had a video here. I put that out of order. I'll have to put that back in order here before I post it. Can I make this big? I'll take the sound off there. So what's going on here is person who's doing this video, they have Coca-Cola or a soda in all 3 of these, and you can see it's the same amount in each one. They put a balloon on the top of each one, and then they also put Mentos in here. All right, and they'll show it to you later. You can't really see it right now, but this container has 1 Mentos, and that's why they're kind of squeezing the balloon. They're trying to get the Mentos to the bottom of the balloon so it falls in. I think you saw it fall in there. All right, so this is 1 Mentos, this is 2, and then this one's going to have 3 Mentos. And I'll skip here because it takes them a long time to get all 3 in there. But as you can see, the balloons start to blow up here. Okay, so we're going to take a look at a specific law now, which is going to talk about how some of those gas properties relate to each other. All right, and as you would probably expect, the one that has 3 Mentos, the balloon is a little bit bigger than the others. 1 is the smallest, 2 is a little bit bigger, and then 3 is the biggest. Now, why is that? Why is more Mentos making a balloon get bigger? All right, so what happens are these Mentos, when they go in here, they start to create a gas, okay? And the more gas that they create, the more particles of gas, the more gas particles, that's our number of particles that we talked about in our notes. The more gas particles that we create, the more they're going to push on that balloon and expand it and make it bigger, meaning that it's going to have to take up more volume. So here, let me move my head here. Okay, we need to use a particulate drawing to describe what is happening to the gas molecules inside the bottle. So I'm going to draw just with this here, but you can draw, or you can find pictures on the internet and upload them here, or you can go to insert a drawing, all right, and you can insert dots in a box to kind of show what's going on here. But before the Mentos, whoops, here we go. Before the Mentos is put in, I have my container. Okay, this is like my balloon. It's an awful drawing of a balloon. Just we'll have to deal with it. Okay, and I'm going to put 5 dots in there. Okay, 5 dots in the balloon. Okay, so even though it's deflated, it's not like it's completely empty of gas. There is some gas in there. Okay, and I'm going to put some speed, some movement on each one in just kind of random directions here. Okay, now let me maybe scroll over here. So I have a little bit, oh, that doesn't work quite as well as I had hoped. That's okay. Now, when we put the Mentos in there, what happens is that Mentos is helping create more gas. So I had 5 dots in here. In fact, what I'm going to do is I'm going to change this color so the dots kind of stand out. Blue dots, red arrows. So I had 5 blue dots. Now I have to have more. Okay, so I'm going to have to draw at least 6 dots. Okay, I'm going to draw 10 just because. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now I'm going to go back to red here. And they're going to have arrows and they're going to be moving, just like the other ones. Now the arrows should be approximately the same length. Okay, so they're approximately the same length here. They're all moving in random directions, but because there's more particles, they need more space to move. All right, and so they're going to make whatever container they're in, as long as the container is flexible, and we'll assume that it is, that container is going to grow. It's going to get bigger so it can contain all those particles. All right, that's what Avogadro's law is saying. So now let's take a look at Avogadro's notes. So let's get a little specific here. Okay. Oh, let's go back here. Here we go. Close this. Oh, here, I forgot this part. As the number of molecules, okay, so we're going to increase the number of molecules because we put more Mentos in there. I'm going to highlight that. You could delete the rest or change it red. It doesn't matter. Okay, what happens to the volume? Well, if we have more particles, they need more space. They're going to have an increase in volume. Let me just make that the same. That would have been fine, but I'll just make it the same. Okay, so as the number of molecules increases, the volume increases because, why does that happen? More particles need more space to move around because gas particles are always moving, okay? I'll take that and I'll highlight that red. Okay, you could have done whatever, it doesn't matter, just as long as it kind of stands out a little bit. All right, so now let's get to Avogadro's law here. So definition, as the number of particles increases, the volume increases. Now here's important, as long as the pressure and temperature remain constant. So we can't be heating anything up or cool anything down, because if we change the temperature, that's going to affect the other variables. We also have to have it in a flexible container, which means that the pressure inside and outside of the balloon will always remain the same. If you have a rigid container, so something that's not going to stretch or get smaller, what could happen is you're going to get something that explodes, and Avogadro's law doesn't it's not Avogadro's law. It's a different law we'll talk about later. But it looks like it's not quite holding true, which it's just not his law. All right, so as the number of particles increases, the volume increases as long as the pressure and temperature remain constant. What's the equation? The equation is volume 1. Okay, now when I get the 1 below the V like that, it's control comma. Okay, control comma, not control period. Okay, so volume 1 divided by the number of molecules, 1, equals the volume 2 divided by the number of molecules, 2. Okay, so now what does the 1s and the 2 stand for? Because we know V is volume and N is number of molecules. I'll take that comma away there. All right. The 1 is just like an initial case, what it was like before the Mentos or before something happened. And then the 2's over here are now in a new case. Something changed. Okay. So the volume changed. So how did the number of molecules change? Okay. So now a drawing. I kind of did a drawing for you before. In fact, if you had a drawing from before, you could just copy and paste it down here. That would totally work. All right, so we're going to have, actually, here's a perfect drawing right here where I have a box. I got 4 particles in there. Okay, and they're moving in random directions. Okay, now I'm going to increase the number of particles. I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're going to have approximately the same length arrow as before because their temperature remains the same. Okay. And the container increases in size because we have more particles, they need more space. Okay. What does the graph look like? So now when we have a graph, we're going to have the volume here and the number down here, and we get what's called a direct relationship, which means if one thing increases, the other thing also increases. So if we increase the number, then the volume also increases, and they also do the opposite. So if I decrease the number, then the volume decreases, which would make sense. If I have a balloon and I decrease the number of particles in there by popping it and letting some particles escape, or waiting a bunch of days and particles slowly kind of seep out of the balloon, we see that the balloon deflates. It doesn't take up as much space as it did before, and so we get a direct relationship. Now, here's a practice problem. I'm going to walk you through this a little bit, okay? So whenever I read a practice problem, I'm going to underline the important parts here, and I'm going to summarize it, because what really bothers me is when I read the same example problem 3 or 4 times, I get frustrated and I want to quit. So what I'm going to do is I'm going to summarize it first, and then I never have to look back at the words again. I don't have to reread it. So there are 2,000, whoopsies. I think I got to do that over here. Okay, so there are 2,000 molecules of gas. Okay, so molecules, that's telling me a count or how many I have. And this is how we're starting. So I'm going to set it up V1, N1, V2, N2. Okay, so I know N1 is 2,000. I'm just going to abbreviate MOL there, okay? In a molecules of gas in a 0.25 liter ball. Okay, so volume could be measured in liters. So 0.25 liters. Okay, you add molecules until the ball changes its volume to 0.5. Okay, so now it got bigger. How many particles are in the ball? So this is what I'm looking for. Okay, so now how do I set this up? Here I'll walk through. Whoopsies. Let me clear. So everything I just underlined and summarized kind of over here, it's going to be showing you in the slideshow here. Okay, so now how do we solve this? Okay, what we're going to do is we have the equation and we're going to cross multiply. So let me change colors here. I'm going to go to blue. So cross multiplying, I'm going to take my V1 and my N2 and I'm going to multiply them together. And I'm going to take my V2 times my N1, and I'm going to multiply them together. And then I'm going to put them on opposite sides of the equation. So I'm going to have V1 times N2 equals V2 times N1. Okay, so now I'll put the numbers in there so you can see it. So V1 is 0.25. N2 is a question mark. You can put an X there if you want, anything, so you know that means that you don't know it yet. Okay, and I'm going to take 2,000 times 0.5. 2,000. I'm running out of room here, 0.5. Okay, now I can simplify that. If you do it on a calculator, that should be 1,000. So let me go back here and erase it. I'm going to say that's equal to 1,000. Okay. So now what's my next step after I cross multiply? Okay, so I did this, I cross multiplied, I put the numbers in here that I didn't put the numbers in yet. Okay, now I'm going to divide by V1. Now, why is that the case? I'll change colors again here. Okay, so V1, whoopsies, I'll do this. V1 is multiplied by N2, and N2 is what we don't know yet. That's our X. So I want to get that by itself. So I'm going to divide by 0.25 on both sides. And what happens over here is it cancels, and I get X equals this. And so all I have to do now is plug that into a calculator to get my result, my answer. And so if I put it on a calculator here, 1,000 divided by 0.25 is 4,000. Let me change colors once more. Okay, so then N2 equals 4,000 molecules. Now I'm just going to do a quick check to make sure that that makes sense. Okay, so what happened, if I go back to the story or kind of reread the story, what happened is I had some molecules in a ball and I added molecules. So I should get an answer bigger than 4,000, or sorry, bigger than 2,000. 4,000 is bigger than 2,000, so that makes sense. All right, so that's all I'm really looking for. Do I expect the number of molecules to go up? I do, and so then I get 4,000 molecules. All right, is our N2. Okay, so now there are other ways to solve it, but I always suggest cross multiplying. There are sometimes shortcuts, but cross multiplying will always work. Sometimes shortcuts don't always work. You have to be pretty familiar with your math. Okay, so now one more problem here. Okay, one more problem, and it's right here. So I'm going to just minimize this and make this a little bit bigger so I have a little bit more room when I'm writing the math out here. Okay, I'll go back to red. Here we go. All right, a balloon with a 1.5 liter, okay, so that's my volume, has a 20,000 molecules of air inside. Whoopsies. Why is that not working? All right, I got it to work here. All right, so N1 is 20,000 molecules. Okay, we add particles. Okay, so we're adding particles. So I know that I should get a number bigger than that in the end. Okay, I'll put N2 over here. All right, we add particles until it reaches a volume of 2.25 liters. Okay, so V2 is 2.25 liters. All right, how many molecules would be inside the balloon when it reaches the 2.25? Okay, so this is my question mark. Okay, I have things set up. Now it's important before you cross multiply that you have it set up this way, V1 over N1, V2 over N2. If you have those things flip-flopped, then the cross multiplying doesn't work because it's not set up like the equation. Okay, so cross multiply here, cross multiply here. So I have 1.5 times my X equals 20,000 times 2.25. Okay, now I'm going to figure out what those answers are. Whoopsies. Okay, so I'm going to do 1,000 divided by, whoopsies, multiply by 2.25. That's 45000, 45,000. Okay, now to get x by itself, I'm going to divide by 1.5 on both sides. So I'm going to divide this by 1.5. That's going to get me 30,000. 30,000. Now, I mentioned before that I was looking for a number bigger than 20,000, and I got one. I got it 30,000. So that makes sense to me. That's my final answer. All right, now that's not it. Okay, let me clear this. That's all the notes, but we got some more things that we got to do here. I've got a simulation that I've got to do. So I'm going to click on the simulation. I'm going to go back to half and half screen here. I'm going to run this sim. Okay, so clicked on the picture. Okay, it's going to ask me to click on something here. I should be clicking on ideal. See if that pops up. Ideal. Okay, click on the particle option on the lower left. Oh, whoops, I said lower left. It says lower right, right here, particle. Okay, add 3 pumps. Let's see here. Add 3 pumps of molecules to the container. 1, 2, 3. Okay. Click the handle on the right side of the container and make it as small as possible. That should probably be handle on the left side. I'll change that right now. Okay, 7. Wait until the pressure reading is in the 30s. Okay, it's in the 30s. Click on the option in the upper right-hand corner. Hold pressure, this one, and then an up and down volume. Okay, constant. Click on the width and the collision counter on the right-hand side of the simulation. Width and collision counter. Okay, add more molecules by pumping. Fill in the chart below with your data. Okay, so number of molecules. I need 150. Let's see, that's what I have right here. What's my width? 5.0 nm. Stands for nanometers, but it doesn't really matter. Volume, is it large, medium, or small? I would say this is small. That is the smallest I could make it. All right, pressure. I'm going to read the pressure here. That's 35 ATMs. And what is this? Number of collisions per 10 picoseconds. So all I got to do is hit play here. And it says 199. Okay. Now I need to add molecules until I get to 300. So I'm going to do a pump. That was 200. Oh, did you see what happened? It got bigger. Why does it get bigger? Because if we add more molecules with every pump, we see that it gets bigger. Now we got to prove some things, okay? So now the width is 10 nanometers, which makes sense. If I add more particles, it should get bigger. What is the volume? It's going to be medium or large. It's definitely bigger than before. I'm going to put medium because I can see I got more particles here, and I'll probably get larger. But I'll see. I'll check later. Okay, what's the pressure? Pressure is 35, which makes sense because we're holding the pressure constant, so it's not changing. And then I got to do this again. Let's see what we get. 259. Okay, so a little bit more collisions, but not that many more. Okay, so now 450. I'm at 350. Oh, it's getting bigger. Whoa, pressure cannot be held constant. Volume would be too large. Okay, oh, so we got here at 450. Okay, so the width is 15 nanometers now. I would call this large. Oopsies. There we go. Pressure is close to 35 point. It's bouncing around. I'll say like 35.1. That's pretty close to what we were having before. Now let's check collisions. 345 collisions. Okay, so now let's take a look at these answers. As the number of molecules increases, so as we did more pumps, the volume also increased. It also got bigger. Let's change it there. Okay, it got bigger. Okay, describe why this relationship occurs using the number of molecules, volume, pressure, and collisions in your answer. Okay, so I would say as we add more molecules, there we go. As we add more molecules, they need more space to move around. If the container changes its size to allow the same pressure, and I'll put in parentheses, pressure is collisions to occur. Okay. I am going to just kind of make this one sentence. I don't need a period there. There we go. And then I'm going to change this to red. I'm going to change all of this to red. And just the things I put in there. I didn't put the title or those numbers in there. And let's see, was there anything else I missed? Oh, this stuff right here. And change this all to red. Okay, and that's, oh, one more here. There's a handle on the top of the container. Slide it open and describe what happens in detail. So if I slide it open, okay, particles are leaving. Ooh, I think I know what's supposed to happen. I think I'm going to change this to 400. I think there's a mistake there. I'm going to change that to 400. Oh, I need to re-click on this. That's the problem right here. This might fix it. Yeah, so as particles leave, see what happens? This starts to get smaller, which makes sense. If this was like a balloon, all right, we are deflating the balloon by letting the particles leave. We like opened it up or popped it. And so now if I close it, it's going to stay. If I pump, it'll get bigger. If I open it, it'll get smaller. Okay. Describe what happens in detail. We'll say once the slide is open, particles begin to leave. I'll say period after that. Begin to leave. Less particles in the container means the remaining particles don't need as much space, causing the container to shrink. Oops. Okay, highlight this. Oops. And I'll turn that red. And that's the assignment for the day. So then you can turn this in through Canvas. You'll have a submit button up here on the right. and you'll be done with Monday's assignment. So hopefully that was helpful. Send emails if you're stuck or have questions. Thanks.